get started. We are going to be doing a new section from chapter 2 today. Let me show you. We are going to be exploring data, or at least features of data. And the two main things we're going to be looking at as far as features go is what's called the shape of the data and extreme values. And we're going to use, well, these are the main ones, but there are other things. We're going to look at how you can summarize your data and visualize it by a thing called a box plot, also called a box and whiskers. Histogram, I'm sure you've heard of. Anybody heard of a stem and leaf diagram? You might have got it in a class somewhere. Kinda, maybe, okay. And then dot plots, you've probably heard of them. Even if you forgot the name, when you see one, you'll know what it looks like. And so imagine you've collected your data, and we're talking quantitative data here, right? Numerical data, right? So you've found out the ages of 100 people. And can you imagine what that would look like? It'd be a big piece of paper, right? With 100 people's ages on it. You know, imagine you were working for a small company and your boss went and said, hey, I'd like to know what kind of, you know, what the age distribution of the people who work here is. And you said, no problem. And you go to your computer and you get their ages and you print it out as a big list of numbers and say, here you go, boss. He's going to look at that big piece of paper with 100 ages on it and say, what the heck is that? I can't make head nor tail of it, and I don't have time to look through it. Would you agree that it would make sense if you could organize the data in a way that would allow you to at least get an idea that there's an awful lot of old people work for us, or yeah, I didn't know that the typical age of somebody in my company is 40, or whatever it might be. So we're looking at how you take this data and you put it into tables and you visualize it. And the visualization are these kinds of things here. Now, once you've got that picture, the types of ways you might describe to other people what you're saying is an idea that's called shape. We'll go into that in a lot more detail, and then extreme values. So the one I'm going to use, because I think it's the shape that you're most familiar with, is a histogram, right? So imagine we had a thing going like this, and this would be the age, and this would be the frequency. Now, if I went and did a single box for all the 21-year-olds and all the 22-year-olds and all the 23, and maybe I've got somebody who's 75 and still works for us, right, a night watchman, right? If I did that and there's 100 numbers here, would you agree that this would not be a very useful picture? Because wouldn't it look like this? A couple of people, nobody, maybe 3 people, nobody, one person, a big gap, you know, one person. I mean, for starters, wouldn't it be very wide? I'm guessing there's probably a range of 70 years, and a lot of them would be blank. And occasionally you might get 2 people who are 27 or 5 people who are 31, but it wouldn't be very helpful. So what you might want to do is you might condense your data, or what we call group your data, to make it easier to visualize. So I might go, okay, from 0 to 10. Well, hopefully nobody works for this company who's a child, because we have laws against that, don't we? And then you go 10 to 20, and 30, and 40, and 50, and I'll have to make this a little bit bigger now, and 60, and 70. And then you would get the frequency, and you might have that, and then it goes something like that, and it goes something like that, and it goes something like that, and it goes like that, and then it finally finishes like that. A histogram, right? Now, if you wanted to know how many people were in a certain age group, like the 30 to 40-year-olds, oh, 15 of my workers are in the 30 to 40-year-old mark. Can you see that you would be able to get a feeling for the age distribution of people who work in this company. So when we talk about shape, what we're really saying is, what kind of shape is that, and how do we describe it in statistics? Now, you might just look at that and say, well, it looks a bit like a hill to me. Well, that's fine, but that's not the word we use, but that's fine. We could call it that, I guess, if we'd started off. So let's talk about what kind of shapes histograms have, at least the typical ones that you get. Right. The first kind of histogram kind of looks like this. Now, it is a hill, agreed, but the main feature of it is, wouldn't you agree that it's balanced? We call this symmetric. So we would say this was a symmetric distribution. So what would that be? An equal number of old and young folk, and then somewhere in the middle, the maximum, the place where most people's ages are, right?
Does that have to be perfect?
No. Good question.
Okay.
Yeah.
Just similar.
It just needs to be close to, because, in the real world, you don't get perfect anything, right? Isn't there maybe a few more on this side and a few less on that side? That's allowed. It's still called symmetric. We never use it, but you could probably say there should be a word here called approximately, just to cover yourself legally, but we don't. We just say it's symmetric.
Okay, thanks.
Now, you might get data that looks like this. Now, in this case, would you agree it's not balanced anymore, right? Isn't there a lot more tailing off this way and not so much this way? Wouldn't this be a company that had a lot of young people? Young, relatively speaking. But there is a long, what we call this thing the tail, right? And it's got a long tail, and this tail is to the right. This is called skewed to the right. So if you have data there, it climbs up to a hill, but it takes a long time on the right-hand side where the tail is. It's called skewed to the right. Of course, you could get data that looked like this. If you had no imagination, what do you think this distribution is called?
Skewed to left.
Isn't it nice when things do what they're meant to do? That's exactly what we call them. So I guess in this particular situation, there'd be a lot of older people working for the company and not so many in the young ages, right? So you'd be looking at 3 different kinds of companies, age distribution wise. Just to give you an example of what that would look like. Do you know, if you look at community college professors and their ages, the data looks like this. So I'm going to make a prediction. And the prediction I'm going to make is that there are going to be a shortage of community college professors in the next 10 years. And the reason is that you see this bump over here? This here, excuse me, I'm going to mute some things. There we go. Is that these people are going to be retiring. I'm actually that guy there. I'll be retiring in a few years. And can you see that there's an awful lot of people going to be retiring in the next 10, 15 years? Just because they're getting old. But do you see there's not enough people to make up the difference? So there's going to be a shortage. Now, if you look at some industries, you'll find that they have this skewed feature. And if you are in looking for a career, you might want to join that one because you'll actually be in a pretty good position. You'll be in a field where there is a big demand because a lot of the people who did that job are retiring. Now, there are other distributions, but the only one that I'm going to look at, or at least give you a name for, is a distribution that looks like that. Now, I've deliberately made it not perfect because life isn't perfect, but aren't pretty much all of these roughly about the same height? A weird distribution. I don't imagine a normal company of 100 people would have that age distribution. It'd be really weird, but I guess it could happen. When you see a shape that looks like that, you will call it a uniform distribution. In this case, the uniform comes from, like people who wear uniforms, right? You all look the same, right? I guess that's probably why they use that term. Are we comfortable then with what histogram shapes can look like and the names that we attach to them? So that's what shape is about, right? When you look at your picture of your data, no matter which one of these four they use, you should be able to tell if it's got a shape, what that shape is. I guess the fifth one is, couldn't it just be random and have no shape at all to it? Can you imagine data's just, there's nothing obvious going on? I guess that would count, but we don't have a name for that, so I won't talk about it. So here,
Well, I mean, theoretically, if it's random, then if you stretch it, if you make the chunks large enough, they would be like the uniform distribution anyway.
oh, just have two groups, two rectangles. So I guess. Yeah, I guess you could, but it wouldn't really be truly uniform in the sense because, yeah, randomness tends to generate a couple of really exceptional hills somewhere, for no particular reason. Okay, here is a dot plot. And this one is meant to be, professor gave a test and the test was out of 60. And in a dot plot, what you do is you put a little circle. And that circle represents somebody in the class who got 10. So here is my dot plot. Yeah, there's a dot plot for you. What shape do you think, out of the list that I've gave you, is that one probably closest to fitting? And remember, you're allowed a lot of leeway. Nothing's perfect in statistics.
Probably symmetrical.
Yeah, I would probably say that too. Now, if you had, I won't put the numbers in because that just takes out a different test. What do you think that one would count as?
Skewed to the left.
Agreed. Are you comfortable with dot plots and how you can look at them? The type of questions you get in homework is what shape has this data? They tend to just give you a choice and you pick the choice and you'll pick skew to the left. And for completeness sake, I'll do the other two. Yeah, skew to the right. Maybe get an extra there. Right, skew to the right. Uniform coming up. Oh, I've just found a quicker way of doing this. Can I just do dots? I don't need all those circles. Much easier. And that's for dot plots. So this one is symmetric. This one is skew to the left. This one is skewed to the right. And this one is uniform. So far, so good. Right. Now, let's look at this thing called extreme values. We use the term outliers. So now, an outlier is an extreme data point that is distinctly larger or smaller than the rest of the data. Outliers cause problems in statistics. We do not like outliers. Outliers tend to distort the information. You'll find out later, for instance, that an outlier will make a mean much bigger than it truly should be when you look at the rest of the data. So if you were trying to imagine what an outlier might look like, imagine I have a histogram and it looks something like this. So it's a pretty random set of data. You see that poor little guy out there? Isn't he an outlier? Outliers don't care what the shape of the data is. Don't outliers only matter in the sense that there is a distinct difference between them and the rest of the data? This one would be a big outlier, right? An outlier that's extremely large. Of course, couldn't you also have an outlier over that side? That would count as an outlier as well. Right now, but later on, we're going to show you a more precise way of doing it. Right now, don't you just eyeball an outlier? So it's a judgment call. So we're going to do a little game. I don't think anybody would argue that this is an outlier when you look at this data, right? I think we'd get a vast majority of you would agree with me. Suppose that that guy was here, right? So he's now here. Is that an outlier? A little bit more hesitancy now, right? But a large number, maybe not as many. Now, if I put it here, is it an outlier now? No. You can have little gaps, can't you? Outliers don't need to be, one little gap's not enough to make you an outlier. Don't you have the key word here is distinctly different, right? Distinctly larger or small. But if that's not one, and that is one, would you agree there's a kind of gray area between those two where you might say, yeah, I think it's an outlier, it just made it, I'm going to call it an outlier. And Tanya's going to look at it and she's going to say, nah, I don't think so. I think it's just a big number, but it's not that big that it should be considered an outlier. So you see how we've got a little bit of a judgment call there. Now, hopefully when you get any homework questions, it will either definitely be one or definitely not be one. Now, if I was doing that same question using a dot plot, now that I figured out a quicker way of doing it, can you see our outlier? You agree? Let me put another dot here. Still an outlier, right? Now, Can you have two outliers? Are both of those outliers? Yeah. It's not exclusive. It's, oh, you're only allowed to have one outlier on the right and one outlier on the left. That's all you're allowed. No, it's not like that. Can you have 10 outliers on the right if you had like 1 million people in your data set, right? You could have a lot of people, but the key to them being outliers is that they are distinctly bigger or smaller. When you describe the shape of something, you will use both these terms. I'm going to put in, because I'm a visual kind of person, I like to draw hills around things. Would you agree that this shape is skewed to the right and has two outliers? Okay. Skewed to the right, you see the tail? With two outliers. Imagine I said I collected data and its shape was symmetric with one large outlier. Wouldn't you be able to kind of visualize what that might look like in a very general way? You would see symmetric. Well, some outlier over there, right? I'm being lazy and not writing the rectangles, but that's quite common. Yeah, there's your rectangles if you need to see them. So the vocabulary that we use here doesn't allow us to describe visual things. If I say to you skew to the right, you've now got an idea of what's going on, right? What it might look like. If I say there's one large outlier and two small outliers, have you got an idea that at the ends there's some weird stuff going on, right? If I say there's no outliers, that tells you something as well, doesn't it? If I say it's symmetric or uniform, you've got an idea of what's going on there. Now, I just realized something. There is another name that is used in some textbooks. And that is that a symmetric distribution is also called bell-shaped. Just in case you see that term. But any questions so far? I know it's a lot of notes.
What if it's large on the outside and small on the inside? Is it still considered bell-shaped and symmetric?
When you say large on the outside and small on the inside, are you talking about the outliers?
Right? No, for example, like if 0 had like 5 and 60 had 5, and then as you worked your way in, it got less and less.
So you're looking, I'll do it very crudely. Something like that?
Yeah, exactly.
Yeah, that is symmetric, but it's not bell-shaped. Bell-shaped is only used for the hill version of that. I could make up a name for that. That's a valley shape. I've just made that term up right now. That's a valley shape, right? Yeah, I'm sure that could happen in data, but none of the questions you're going to see looks like that. But yeah, it could happen. What would that look like? That would have to be a situation where you are definitely for something or definitely against something, and not many people sitting on the fence. You know, that kind of. Yeah, I guess it could happen. I'm sure it does. Okay, any other questions? That was a good question. Any others? Right, quick recap of what we should know right now. We really have just been talking about how you visualize data, and we talk about the shape of the data, and we've now talked about dot plots and histograms in particular, and outliers. That's about as far as we've gone. Now I'm going to talk about what's called a 5-figure summary and the shape that it generates. Pardon me, called a box plot. So here we go, 5-figure summary. That's a U, by the way. 5-figure summary. But the way I'm going to do this is by actually creating from a set of data a 5-figure summary. So imagine that you actually, let's pause a minute. Let's use real data. If you are comfortable with sharing, I'd like you to take part in this. So just give me a few seconds to open up the class. Right, I've got the class opened up here. Now, the data I am going to collect is the number of siblings that you've got. So I want you to count yourself and any brothers and sisters. Now, to make my life easy, I'm going to be lawyer-esque about it. You may have half brothers and half sisters, and I'm not offending people because that's the term I use back home. I don't know if they've got a politically correct term for that. If it offends people, I apologize. So just your natural mother and father, right? Same mother and father, brothers and sisters. That's the ones we're going to count. So if you have stepbrothers and stepsisters or half brothers and half sisters, they don't count, right? And we are going to collect all your data, and I'm going to be putting it down here in a few moments. And we are going to make a 5-figure summary out of it. And then I'll show you how to make a box plot after that. So if you don't want to take part, you just don't answer it. So the way we're going to do it is, do you know that little thing where you stick your thumb up, you know? So how many of you are an only child? Stick your thumb up if you're an only child. They're just you. Oh, you're doing it visually for me. Thank you, Tanya. That works. Okay, how many? It's 2 people, you and the brother, you and the sister, whatever it is. Okay, we got 1, 2, 3, 4, 5 of them. So I'm writing them down. 1, 2, 3, 4, 5 of them. Okay, 1, 2, 3, 4, 5, 6. I missed one. Okay, how many of you have 3 in a family? 1, 2, 3 of you. How many have 4 in a family? 5? Ooh, 6. Cool. Oh, 2 of you.
Is it just siblings?
Yeah.
Like, are we just counting siblings, or are we counting like parents? Because the total there's 7 of us, but I only have 4 other siblings.
Okay, so you're actually going to be a 5 then. Any 7s? 8s? Oh, David, what you got?
7.
7. Okay, I wasn't sure if it's 7 or 8. 8s? 9s? Yeah, there's me. I'm 1 of 10. Oh, Daniel, are you a 9?
Yeah, 9.
Cool. Isn't having a big family fun?
Yeah, my great-great-grandfather was 1 of 18.
Oh, God. That is a lot of people.
I don't think big families are fun. I always lose my clothing. My siblings go in and take all my clothes. It's annoying.
I think that's a girl's problem. I don't steal my sister's clothes, so that was okay. And my sisters never stole my clothes, so we were good. I was unfortunate enough to be born with, the first one in our family was a boy. My mum then had 6 girls, and then she had me and my little brother, and then she finished with a girl again. So I can imagine sisters losing stuff, but I never had people wanting to steal my clothes problem. So I'm kind of different from you, Alison.
No, my brother takes my pajama bottoms. That's about it.
You realize that is TMI, and if this ever gets out, he is going to be really annoyed at you. Okay. So let's return now. So we've basically collected some data here, right? Now, let's pretend, I think it's a reasonable assumption, that this class is typical OC student kind of class, right? So you lot are kind of going to represent what an OC student class might look like. So the first thing I'm going to do is count how many data points we have. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. We've got 15 of them, right? So n equals 15. What we do in a 5-figure summary, the first thing you get, so the first thing you find is called the median. It also has a weird name. It's also called Q2. So there are 15 numbers. So half of 15 is like 7 and a bit. Would you agree? 7.5. Now, if I count 7 from this side, 1, 2, 3, 4, 5, 6, 7, I get to here. And if I count 1, 2, 3, 4, 5, 6, 7, I get to here. Do you see that this guy here is right in the middle? The median is the middle number when you put the data in order. Would you agree that 3 is, right, there's 7 numbers this side, 7 numbers that side, and that's right in the middle. That is called the median. We're cool with how that was calculated. So I'll write the guy down here. This is one of our 5 figures from the 5-figure summary. Now, there's going to be a guy up here called the minimum, which in this case is here. So I'll call that Q2 because it's just easier. This is going to be the minimum, right? And this guy here is going to be called the maximum. So far, so good. That's 3 of the 5-figure summaries. And then we have a guy here called Q1. And we have another guy here called Q3. And this has a name. It's called the first quartile. And this is called the third quartile. All right, let's figure out how we are going to get Q1. Right, you've got your data, and right in the middle, you've got the median, right? Now, doesn't that break the data into the bottom half with all the small numbers and the top half with all the big numbers? Q1 is the middle of this group. So let's see what we have. 1, 2, 3, 4, 5, 6, 7. If you count the middle, would you agree that one there is right in the middle, isn't it? And that guy there is going to be called Q1. And if you go on this side, you've got 1, 2, you get the same amount. So 1, 2, 3, 4. Would you agree that that guy is the middle of the big numbers? So Q1 is called 2 and Q3 is 6. Now, if you want to think about why these are called quartiles, here's the reason. If you go from here to here, right, from the beginning, the minimum to that guy, you have basically got a quarter of the data. Right. 25%. So in other words, 25% of this class are roughly, very roughly, because it's a small data set, have 1 or 2 people in their family. If you think about the third quartile, from here to here, right, from the minimum to that one, that's 3/4, right? It's called the third quartile, 3/4. So 3/4 of the data, or as I prefer, 75% of the people in this class are in the range 1 to 6 in their siblings. What percentage is from the beginning to the middle on number 3? What percentage of the data should be in the range 1 to 3 siblings?
50.
Can you see why it's sometimes called Q2? The second quartile? Well, isn't 2/4 just 50%? So I mean, the name's not 100, that weird. So this whole thing is called a 5-figure summary. It's quite a nice way of taking a lot of data and basically summarizing it into just its key features. So there's a shape over here called a stem and leaf. Sorry, a box plot. Forget what I just said. It's called a box plot. Looking at the wrong thing. That uses this. So let me show you how you create a box plot of this. The data I have got goes from a minimum of 1 to 10. So you draw what's essentially a ruler. You can put more numbers in if you like, even if they're not used. And that's your starting line. You draw a ruler You then, the minimum is at 1. So you do a little baby mark at 1, and the maximum is at 10, and you do a little baby line at 10. You do 3 longer lines at the quartiles. So at Q2, you do a guy that looks like that. At the median, you do a guy that looks like that. At Q3, you do a guy that looks like that. I may have screwed up a little bit. You then join these guys together, and then you join this guy to the end, and that guy to the end. And that's what a box plot looks like. Right, now that you're seeing one, have you seen one in maybe a chemistry or a physics or a geography class? Have you ever seen pictures that look like that somewhere? That's what a box plot is. That's where it gets created from. It gets created from the original data converted into a 5-figure summary. And from that 5-figure summary, you draw this picture. So what we're now going to do is we're going to go back and look at, in particular, shape. We won't talk about outliers. It's kind of hard to tell if there's an outlier here, so I'm not going to even try. But we're going to look at shape. So I might as well use this pen, it's nice and thick. Suppose I do a box plot and it ends up looking like that. Is it, and you're only going to get really 4 choices here, right? 4 choices. Symmetric, skewed right, skewed left, or no shape at all, right? That's it. Symmetric, skewed left, skewed right, or no shape at all. What do you think that one is? I hope it's obvious.
Symmetric.
Symmetric. And it would be symmetric if it was a hill, right, a bell-shaped. It would still be symmetric if it was, you know, the one I made up the name for, the valley. They would still look like that, right? That's what symmetric looks like. Same choices. What shape is that data?
Skewed left.
Correct. Why? What made you decide that?
Because the left side is longer than the right side.
Right. You see the box is bigger on the left than the tail. This basically is where the tail is, right? The next one will be a giveaway based on what I just did. You see what skewed to the right looks like? So you might think, what does it has no particular shape, at least a shape that no one has given a name for. Well, can you imagine a shape that might have a very long tail to the right, but the box is on the left? You see there's a contradiction on which side the data is bigger. You see here, big tail, big box. Big tail, big box, right? That's skewed left, big tail, big box. Skewed right, big tail, big box. Oh, big tail, totally different end, big box. You see they're contradicting each other? I'll just call it no name because it doesn't have a name that I can tell you. Are we comfortable with 5-figure summaries now? And how, once you've drawn the picture at least, you can now tell me what kind of shape it's got, and that's about it. If you were talking about outliers, wouldn't you probably have to go and look at the original data and say, oh, you know, like your great-grandfather, was it 17 or 18? Someone mentioned a family that was as big as that. Right, if that person was actually here with bottom pattern time, wouldn't 10,18 probably mean 18 was an outlier? Would you agree it's definitely bigger than the rest of the numbers? But you just have to do that from the raw data. You can't really tell outliers when you look at these box plots the way I've drawn them right now. Would you agree I don't know if that's exceptionally big. Couldn't there be lots of numbers all the way up as well? You can't tell. Which brings me back to ours. How would you describe our picture, our data, this class? Which one? I see nods, but no answers. What's this one?
Skewed to the right.
Agreed. Big tail, big box. Agreed. Big tail, big box. That seems reasonable. Would you agree? There's more room to have big families than there is to have small families. Right? If you're going to have a small family size, doesn't the answer 1, 2, or 3, right? You don't have a lot of room to spread that out. I guess you could have countries in the world, and I'm sure there are some, where small family sizes are rare, right? So they're all strung out, and everybody has a huge number. I'm from a generation very similar to one of our students. My dad was one of 8 children. My mum was one of 15. So we come from, that's what was kind of maybe slightly on the large side, but that was typical of our day. Just to share with you, my dad had a very simple family. It was one mum, one dad, all shared the same children. My mum's life was quite extreme. Her mum, she's the oldest in her family. She was the firstborn, and she had a smaller brother. And then she had, her mum had a daughter and died in childbirth. So my mum was 12 years old, and in those days, you left school if that happened. So my mum basically became a mother. She looked after her baby sister for a few years. And then her dad married a woman who had, I think, 4 children. She was widowed. And so she inherited some step brothers and stepsisters. And then they had their own children. So when I was growing up, we didn't call them step uncles and step aunts, but my mum had step brothers, step sisters, half brothers, half sisters, brothers and sisters. It's a pretty complicated family. But in today's world, that's not common. So are we good with these guys? Can we move on to the next piece?
I had a question.
Go, Tanya, what you got?
So the no names box plot.
Mm-hmm.
Well, I guess first I should ask, are the graphs interchangeable? Like if we have the same set of data, we can use either one?
I'm not sure what you mean if we have the same set. Oh, do you mean can we use a histogram, or could we draw a box plot of it or whatever? Yeah, you could, but in the homework they just actually, in a lot of the questions in the homework they just show you the darn picture, so you don't even need to create them. Okay, or you hit a salt button and they do one.
I guess I was wondering if the no name box plot was the equivalent of the uniform, or if it was something other, like the histogram. No. If
it was uniform, it would look pretty much like that, right? It would look symmetric as a box plot. So the no name one wouldn't necessarily be that one. So if we are good, can we look at the last kind, which is the stem and leaf? We've got time. I'll try. Stem and leaf. How do you create them? And then once we've created them, we can talk about if we have time. If not, I'll do it tomorrow. A stem and leaf diagram is just another visualization of data. So let's imagine that we had some data and it was the ages of people. If I had time, I'd actually collect this class's ages. That might be a good idea, actually. Okay. I want you to say your last name. Type it in under chat, because that's attendance. Right. So I'll give you a few seconds to do that. And while you're doing that, I'll set up our data set. And what we're going to do is we're going to get your ages. And I think the quickest way for me to do that is in chat. If you want to take part, you do. And if you don't, you just don't do anything. Type in your age. So just type in 14, not just 14, but you know, type in your age and hit enter. Okay. And I'm going to write down the data as it has appeared. There I am. Right. Okay.
You guys 66?
Yes, that's my age. You are meant to be amazed at how young I look, right?
There was another 16 that just appeared, I think.
Right. So I think we've got everybody's data that wants to take part. And that is good. So can you imagine that if you could do that as a histogram, I guess? Can you? You'd probably have to group them in some way. You could certainly do a 5-figure summary and then get a box plot, and I could do a dot plot as well. I mean, there's lots of ways of doing that. But we're going to do a thing called the stem and leaf. And we know we're not. But tomorrow we are going to do a stem and leaf.